Thank you very much, Philippe, and thank you also, Professor Cittadini, for the very kind invitation to be at this quite remarkable meeting. It's a huge honor to see my name on this list alongside some really true greats in our field. So I've been asked to talk about this rather challenging topic of the role of the embryo and endometrium in human implantation. And normally when you have a conversation like this with colleagues, particularly our colleagues in the lab, it's a fairly short one, that the main determinant of implantation is probably the embryo. This is expressed in a characteristically succinct way by David Baird at a meeting I was at in Cape Town in 2006, but I think it summarizes actually a large body of literature. The trouble is that there is increasing evidence that there's more to it than that. And I think the evidence for that comes from the ongoing discussions that are happening about how we improve IVF outcomes with all the latest technologies that are coming in. And certainly they are improving it, but we have to accept that the focus on the embryology is giving us diminishing returns for investment. As we're getting better and better at culturing embryos and at selecting embryos, we need to invest an awful lot more to get any real improvement in outcomes. And this is what we might call the law of diminishing returns. And therefore, even though I will accept that without a good embryo, you're going to have a hard time creating a pregnancy, I think the time has come, now that the field of embryology is so mature, for us to focus on what I will admit to be perhaps the second partner in this, but one which I think could be the area where we're likely to make real strides in improving outcomes. And the discussion we just had about the endometrium and the oocyte as the factor determining health of the child is a good example of that. So one of the slightly depressing things when you work in endometrium is to compare our kits for measuring endometrial receptivity with what they have in the lab. And even just looking at ovarian function, sperm function, it's a very sophisticated area of investigation. And essentially, when you look at how we assess endometrial function, it comes down to this. A little measurement of a little white line using ultrasound at the limits of its resolution to determine any difference anyway. And therefore, it's not surprising that when you look at the predictive value of this kind of test, it's rather disappointing. And if you can construct an ROC curve, as Frank Broekmans did after looking at the literature, looking at the relationship between endometrial thickness and outcome, really only at the very extreme thinness is it really having any predictive value. And in fact, the frequency at which we see these very thin endometria is quite low. And yet probably the endometrium is contributing in far more cases than indicated by this very crude assessment. So we need to move on from this. And so over the last few years, there's been a number of investigations to see, well, look, can we look at endometrial function rather than just appearance? And this is a study from our own group where we looked at endometrial gene expression in women who'd had recurrent implantation failure of unknown cause, but where the embryos that had been transferred were at least morphologically normal. They weren't subject to chromosomal analysis, which could be seen as a weakness in the study. But even with that weakness, we were still able to identify a group of women where there seemed to be a clear problem with the endometrium as expressed by abnormal gene expression. And when you look at those genes that are different in these women, interestingly, they tend to be associated with processes more akin to the follicular phase rather than luteal phase. So this idea that everything happens in the implantation window is the only important part of endometrial function needs to be questioned, because in fact it looks as if things start going wrong far earlier. And when you validate this sort of profile as we did, and you look at its predictive value, then you find actually there could be some value in this, that the ability of a gene classifier to predict the phenotype of recurrent implantation failure seems to be very good. Now, having said that, there will be a lot of women with recurrent implantation failure who will have normal endometrium, and I'm very happy to admit that in those cases an embryo factor could be present. But it does at least make us stop and think about whether we should just be focusing on the embryo in implantation or whether or not there may be endometrial functions that we should be considering too. So let's start with a very basic question. I think one that we often forget when we think about this, that once we put an embryo into the uterus, we don't really know what happens to it. All we know is whether or not the woman gets a pregnancy test or not. And it could fail at several steps. It could be that the endometrium's perfect, but the embryos failed to thrive in utero. The embryos thrived, but failed to initiate implantation, or that the embryo has initiated implantation, but failed to complete it. And this is a big black box, as we described a number of years ago, that really we don't know what's going on. So in order for us to intervene, we've got to really try and open this black box. Now, the first person to literally open it was a long time ago, way back in the 50s, when John Hertig published a sort of paper that we just wouldn't be able to get away with now, ethically. He asked patients who were coming for a hysterectomy for benign indications if they wouldn't mind just having intercourse a couple of days beforehand. And he timed the hysterectomies to be in the luteal phase. So once he'd removed the uterus, he then looked inside, literally opened up the black box, had a look inside, and amongst about 100 uteri from patients who were thought to be fertile and had had intercourse a few days beforehand, at the fertile time of the cycle, he could only find a very few concepti, and even those he found didn't look very good. So this was the first indication that the human species is not very good at producing healthy embryos cycle to cycle, when you go and look at this in the crude way. And he raised the question as to why is this happening? Well, I'm going to talk a little bit about why it might be happening. And I'm going to start with this figure, which many of you will have seen me talk about many times. It's basically the summary of our black box paper, and is based on previous work by Tim Chard. But what it tries to visualize is this idea that human conception and human pregnancy are two very different things, and that only a proportion of human conceptions result in a clinical recognizably risible pregnancy. It's sort of above the waterline, we might say, in an iceberg metaphor. So what the woman sees are just about 40 or 50% of the embryos that have been formed, and most of these have been lost before she has even missed a period, had a positive pregnancy test, or even become excited that she might, or depressed that she might be pregnant. And more recent analysis of this have shown that there's probably around about 50 to 70% attrition of embryos in spontaneous conceptions, which is clearly raises the question as why is this the case? Well, why is there such a high rate of implantation failure? Is it the embryo? Is it the endometrium? Or is it both? Let's go back to some old data. And this, you could bring it right up to date and refine. But essentially, the problem we have as a species is that we produce a high rate of meiotic areas in our embryos compared with other species. And this presents the mother with a problem, because many of these embryos will still be invasive, even though they're chromosomally abnormal, and the work of our colleagues in PGS over the last few years has refined our understanding of this. But she's dealing with it. She is dealing with it. And although she's having to lose a lot of these embryos, it does mean that by the time the baby is born, it's most likely to be chromosomally normal, having started off with perhaps only 4%. Depends where you look and how you define this. But the paper published in Nature Medicine 2009, where they looked at every chromosome in every cell of human day 3 embryos, the presence of at least one abnormality was extremely high, such that almost all embryos had something wrong. And yet at the other end of pregnancy, of course, hopefully the babies are normal. So there's something going on there which is selecting this out. And what I'm going to talk to you today is some work we've been doing over the last 10 years, which we started in Utrecht when I was working with Bart, where we're looking at the endometrium and we're able to describe what we've called a biosensor function for this organ. And the idea is that this biosensor function is allowing the mother to deal with this attack of invasive but potentially poorly viable embryos. So she doesn't invest in a pregnancy that's unlikely to end up with a good result. And if you think about it in those terms, it almost becomes a requirement. There must be a biosensor there. So you can go and look for it. Well, of course, we never think of those terms. That's how we think of it in hindsight. But at the time when we started doing this study, and this is one of my PhD students, Gijs Tecklenburg, that was doing this work, we were simply looking at whether or not there were any signs of response of the endometrium to the quality of the embryo, and we expected that the response would be high in the presence of a good quality embryo and low in the presence of a poor quality embryo, because that's the paradigm we've all been brought up to believe. And we found the opposite. What this figure shows that when you co-culture a good quality embryo, with stromal cells that have been decidualized in vitro, they hardly respond to it at all. They're completely unimpressed. There's really no change in the production of a whole range of cytokines. But when you co-culture a poor quality embryo with these stromal cells, they do stand up and listen. And we observed a marked downregulation of a whole range of growth factors and cytokines in response to the presence of a poor quality embryo. It's just stromal cells, just in vitro, but an interesting and clearly important compartment of the endometrium as part of implantation. And of course, there are other ways of looking at how the embryo and the endometrium will interact with each other. And my next PhD student, Lotte Weimer, set up these co-culture models where we took stromal cells, decidualized them in vitro, put a scratch through the cells, which you can see is this big gap here, and you can place an embryo in that. And you can just watch what happens. You can watch how the embryo and the cells interact. And for those of you who haven't seen this before, it would be reasonable to expect that what we will see, if I can run the video, is that the embryo will settle down onto these cells, spread out, and start invading, because that is our paradigm for implantation. So if it's going to work, you'll see that what we absolutely observed was slightly different from that the embryo was just sort of floating around in there, but the cells were doing the work. They detected that the embryo was there and started reaching out towards it, engaging with it, and even beginning to, with the eye of faith, embed it, bring it in to the stromal cells. Well, this is a rather shocking finding because it tells us that maybe it isn't just the embryo stupid. It is the endometrium as well that is depending in its response to the embryo, but is in fact an active partner in implantation. And I think if we accept that paradigm, that opens up a whole range of possibilities for us as doctors and embryologists to intervene. So what happens when it goes wrong? Well, if you put a poor embryo there, then you can show that the migration of cells to that embryo will be different. So this is a study that Lotte did. In the left panel, you see the movement of cells after 18 hours when no embryo has been placed there. There is an artifact there. It's not an embryo as far as I know. A high-quality embryo is placed in panel B, and then you can see the migration that I showed you in the video. But if you put a 3PN embryo and a very poor one there, you'll see no response to that. There seems to be something about the presence of that embryo which the cells are recognizing and responding to by not engaging with it in that migratory fashion. So it does look that with these two approaches that there may be a biosensor present in the decidualized stromal cells that could be contributing to this prevention of the mother investing in poor quality embryos. So she must be listening out for some sort of distress signal from the embryo. Do embryos produce distress signals? Well, if you read Henry Leese's work and take on board this concept that the high-quality embryo is metabolically quite quiet, it doesn't need to do much, it just needs to grow, and therefore produces fewer metabolites, you can also assume that the very poor embryo is fighting for its life, it's undergoing through apoptosis, it's having to undergo repair mechanisms, is producing a lot of metabolites, and this has been shown, which could potentially be recognized by the endometrium as a sign of a poor quality embryo. And again, controversial work still, but this concept that the failing embryo or the poor quality embryo has more mitochondria would tend to support this fact that they are metabolically more active and more noisy, if we can call it that. So how does the endometrium respond to that? Well, if you look at gene expression level in the endometrium and you co-culture endometrial cells with culture medium that's been conditioned by good and poor quality embryos, what you'll find is that the gene expression in those endometrial cells will change very little when you co-culture them with good quality embryo culture medium. In other words, culture media that's had top quality embryos in, you put that into the culture with the endometrial cells and you look at gene expression, hardly anything happens. But if you do that with conditioned medium where poor quality embryos are sat, then you see a very different picture. You see a very profound dysregulation in the gene expression in these decidual cells. So up there we see the DIE, developmentally incompetent embryos, 447 genes dysregulated. Developmentally competent embryos, hardly any. So this does raise, again, more evidence that there may be some process going on which is allowing this biosensor to function. So how does the endometrium recognize the incompetent embryo? And it's a difficult area to investigate. You have to use in vitro models, mouse models, and that's what we did, working with Jan Brossen's group in Warwick a few years ago. And to draw the conclusions together, what we proposed from this work was that, yes, there is a biosensor. It resides in the stromal cell compartment, that the embryo comes into the uterus. It engages in the traditional positive way with the epithelium. In other words, the better quality of the embryo, the more likely it is to oppose and adhere to the epithelium. But it's also sending out some markers which the epithelium detects, and one of these is probably trypsin or proteases, which in certain quantities produces an influx of calcium into the epithelial cells, which send a message down to the stromal cells, this is a good embryo, let's nurture it. But what we found is that poor quality embryos were causing a very different trypsin level and different calcium oscillations pattern, which we have hypothesized causes an endoplasmic reticulum stress response, ultimately leading to menstruation. This is work that needs to be confirmed. There's work ongoing to look at whether these mechanisms are indeed as we hypothesize, but it would seem to be a potentially fruitful route of research. But as clinicians, if we believe the biosensor function, what might be going wrong if the biosensor doesn't work? Well, one could go back to that figure and say, well, if the woman is less good at selecting out these embryos and allowing, therefore, poor quality embryos to implant, her iceberg of pregnancy will rise out of the water in the sense that many more of these pregnancies will become visible to her. They will stick around long enough to cause a positive pregnancy test for her to miss a period. But of course, they're not viable, so they're going to end up as a miscarriage, which is not good news for her. It might mean higher pregnancy rates, but it's not going to mean to more babies, and it's going to lead to a lot more upset. So if you do this experiment again, and you take stromal cells from women with recurrent miscarriage, then what you find is, yes, actually, they're not so good at detecting the presence of a poor quality embryo. In the panel below, we've got the same experiment run as the first one I showed you, but in this one, the stromal cells are from women with recurrent miscarriage. And on the right, you'll see that in the presence of a 3PN embryo, rather than the cells staying away, as you see in panel C, in panel F, the cells are engaging with the embryo. Now, small study, in vitro, etc. But I think it does support this concept that one possible cause of recurrent miscarriage is failure of the biosensor. And it's something that our colleagues in recurrent miscarriage have not yet looked at as a possible cause. So we can therefore envisage, perhaps, there is more to the endometrium than receptivity, that it may also have this selectivity function. And when that balance of receptivity and selectivity is out, it could end up with pathology. So in other words, if the woman is too selective and not receptive, she may present with recurrent implantation failure, for instance. On the other hand, if she's too receptive and not selective enough, she'll allow these poor quality embryos to implant, and this will lead to miscarriage. And this study from America has suggested there may be something in this. They were looking at this concept of superfertility. In other words, women who constantly get pregnant very quickly, what happens to them? And what they found was that quite a large proportion of women with recurrent miscarriage are actually conceiving very regularly. And that they calculated around about 30% of women with recurrent miscarriage, this is where the problem lies. Is something wrong with their biosensor function. And our own clinical study looking at time to pregnancy in women with recurrent miscarriage has certainly supported this concept. It's an area which has not been addressed at all by the recurrent miscarriage community yet, but I think it's one that we probably should be looking at. And just as I come to a conclusion, I want to bring this a little bit further in terms of possible clinical implications, and this is speculation, what I'm going to show you now. We're all very focused on this increase of aneuploidy in embryos as women get older. And we see that reflected in the miscarriage rate. And the assumption tends to be that the rate of aneuploidy in embryos is basically the younger you are, the lower, and the higher you are, the older, and therefore that's why you see a miscarriage rate go up. But there is actually discrepancy there, and this is a figure that Eva Hoffman lent me, which she produced with Alan Handyside for a recent book chapter. And I just found it very intriguing, because if you look at the rate of aneuploidy in implantation, pre-implantation embryos, it's more of a U shape. So younger women, perhaps not yet with a fully mature ovarian pituitary hypothalamic axis, seem to be producing more aneuploid embryos than women, say, 28 to 30. But when you look at their natural conception rate, their clinical conception rate, and miscarriage rate, it is not higher. In other words, they seem to be dealing with them better than older women. And so I want to propose today is that one reason why women who are older get more miscarriages is not simply because the embryos are not so good, but the biosensor may not be so good either. And there may be, therefore, an aging factor to this function of the endometrium. Speculation at this stage, but something I think that's eminently studyable, and I hope we can do that very soon. For the IVF people amongst us, what might be the implications? And the question I often get asked is, well, if you've got one good embryo and one bad embryo, and the uterus is sensitive to the presence of a bad embryo, should we just transfer, and we've got two embryos, one's good and one's less good, should we just transfer one? Because maybe if we put the other one in as well, the uterus will go, no, I don't like this, and won't allow the other one to implant. And I always used to have to come up with some sort of speculations on that. And then this paper emerged from Nick Rain-Fenning's group, which I think is quite intriguing. Presented at BFS last year. I don't think it's yet published, but hopefully it will be soon. And they looked at their outcomes in women undergoing single embryo transfer and double embryo transfer. And they looked at their outcomes depending on embryo quality. And what you'll see from this, if you start on the left-hand side of the panel looking at the data on single embryo transfer from about 800 women, if you transfer a good quality embryo, an elective single embryo transfer, you're going to get a high clinical pregnancy and a high live birth rate, as shown in the green there, which we know. And if you put a poor quality single embryo back, which will often not be elective, because it will be the only embryo you have, the outcomes are very poor. Well, we knew that. Let's go then and see what happens if you put two embryos back. Well, if you put a good one and a good one back, they were getting very good results. Not much better than single embryo transfer, you could say, and at the cost of a huge multiple pregnancy rate. And when they put two poor ones back, yes, also poor results. But ask you to focus on the middle one, good and poor, depending on how we define that. But what they found was if you put a good one and a less good one together, the outcomes are less good than when you just put a single embryo transfer back. But when you do get a pregnancy, you're more likely to get twins. So for me, this is very helpful in counseling patients because they do understand this concept and how might it work, and that would tend to support the data that we see here. So to finish, Mr. Chairman, I think we need to reassess the endometrium as being more than just a receptive, a passive player in implantation. The embryo, of course, is crucial, but the endometrium has a key role in determining whether or not an embryo will be permitted to establish a pregnancy. And so we've developed this idea that, yes, we have these different windows, if we want to call them that, in the cycle. We have a fertility window around the time of ovulation. We have an implantation window when the endometrial will be capable of accepting the implantation of an embryo. But there's also a selection window, which seems to be transient, such that when an embryo implants out beyond that window, the biosensor is no longer functioning, and she's more likely to end up with a miscarriage. It's been shown by Adam Wilcox and others. So let me conclude. There's no doubt that for the first 40 years of IVF that we're celebrating here today, the embryo has rightly been the focus. The key challenges that Bob Edwards and many people here today faced and dealt with was in allowing clinicians to be handed a good embryo to transfer. And that's what we get in most cases now. But the investment we're making in trying to improve outcomes in this, I'd say, are diminishing rapidly, and we're having to spend more and more to get smaller and smaller benefits in outcomes. And therefore, I think the time has come to move to the endometrium. It may be cost-effective to do that now. One aspect of endometrial function, and many others I could have talked about today, but we've focused on the biosensor, one that's emerged as a key determinant of successful implantation. And when you think about it, it is needed. the mother does need that. But there's still a research need to further understand how that signal is detected and responded to, and Jan Brosen's group is still working with us on that. And we also, in Copenhagen, looking at trying to develop biomarkers of decidual function to see if we can identify through a simple test whether or not the decidualization is the problem in that patient without having to take a biopsy. And I suppose the promise of this, and it's still just a promise, but I think it's one worth pursuing, is that if we can modulate this biosensor, it opens up completely new routes to help women with recurrent miscarriage, help women with recurrent implantation failure, and possibly even fertility. And I'd just like to finish by acknowledging these different groups. Up at the top, the group I work with to develop this concept of the biosensor. In Southampton, our group is working at other ways of measuring the uterine function using novel techniques to do so. And the lower group, we're working on biomarkers for decidual function, which I hope will be clinically useful. Thank you very much.